Okay, so in this video, now I am going to derive how to calculate the confidence interval, right? So first, I will fix the confidence level at 95%. So you may choose 99%, 90%, or actually you could choose any percentage, any probability, depending on your willingness, like how much you can accept the error probability. So like 97%, 98% are also fine. But the typical most common choice is 95%. So I am going to derive the confidence interval based on 95% first. And I will fix the parameter to the population mean. So you can think about different parameters like variance, probability, median, other percentiles, but uh, actually they are similar but different, but more difficult. So we are going to restrict our attention to only to the population mean estimation. So we would like to estimate the mean. And this is applicable in many applications. So I guess at this level, this should be sufficient. And then if I fix the mean as the parameter, then automatically we learned the best point estimator is the sample mean. We learned that. So I'm going to use x bar as the center of the interval because the point estimator is minimum variance unbiased estimator. That's what we learned like earlier this chapter. Then what remains is the margin of error. If you calculate the margin of error m, then you can just simply subtract and add the margin of error to the point estimator, sample average. So now the derivation of confidence interval is simply the a derivation for the margin of error that satisfies this confidence level. Okay, let's see. Then the clue we have is the 95%. We learned it was a trade-off. The confidence level and the margin of error are trade-off, but this is fixed. So we have to start from that. Confidence level is fixed at 95. So we are going to start from this, and you can write the confidence level this way. So 95% is the probability that your interval correctly contains the true parameter, right? Do you remember the definition? So your interval is x bar, the sample average, minus margin of error, plus margin of error. And in between them, the true parameter must be in between them, right? So its probability should be 95%. So remember, so mu is non-random true parameter, the population mean. Even if you don't know that, but it is there, it is fixed. That's your target, and m is what we'd like to calculate. We are solving this equation for m. Therefore, inside the probability, the only random guy is the sample average. Like we learned why the sample average is random, and this is the only random guy. Mu is a parameter, so it is not random. M is unknown. We are calculating for, so it is not random. So the random thing is only x bar. So because x bar is the only random object inside the probability, we are going to rearrange the terms so that in the it comes to the center in the middle. So x bar is isolated in the middle, and then it is equivalent so subtracting x bar from all three terms and then subtract mu from all three terms will give you this. I won't derive it in detail. Must be simple enough to see. So anyhow, so this is what we want. We know, and then it is random. And you remember, you may see the idea. We learned the approximate distribution of x bar in the previous chapter. Sampling distribution chapter told you x bar will be approximately normal. That's how we are going to calculate the probability. So remember, the mean of x bar sample average is the mean of single outcome, which is denoted as mu. And the standard error of x bar sample average is the standard deviation of a single observation divided by square root of n. Remember the difference between sample average and single observation. Their standard deviations are different but related by this formula. So if you denote the standard deviation of a single observation as sigma, then you can write this way. And by the central limit theorem, x bar is approximately normal distribution, and the parameters are already given. Mean is mu, and standard deviation is sigma over square root n. So that means variance is sigma squared over n. And then I'm going to do the standardization here. Standardize. Subtract the mean and divide by the standard deviation. Then you get, so in the place of mean, you have mu. And in the place of standard deviation, you have to have sigma over square root n. Remember, this must be standard deviation of the original variable, I mean x bar, because it was normally distributed, but it was non-standard normal distribution. So you have to use the parameter for the normal distribution in the standardization. And we know this is standard normal distribution because that's why we are doing this transformation. Okay, so now we are ready to calculate that probability. So previously we wrote down this probability. We want this probability equals to 95%. In other words, we would like to find m, the margin of error, that makes this probability equal to 95%. Okay? So then, like in this form, randomness was on x bar, but it was normal distribution. So we would like to do the standardization first. And remember, for the standardization, you have to balance each term, like by doing the same thing here. And mu is cancelled out, which is pretty good because actually this estimation problem is about mu. We would like to estimate mu, but in our calculation, in our algebra, we need to know mu. But fortunately, we don't need to because it is cancelled out. So mu is cancelled out, and the middle term becomes z, standard normal distribution. So in the end, we have this standard normal probability. And what it has is so something minus something plus something. So z, standard normal distribution, is contained within an interval plus minus something, and that interval must give 95%. So we have to find an interval from the standard normal distribution that gives 95%, which we have done as an exercise in chapter 6, 5, like 6, right? So we are looking for this guy. We want a number a such that standard normal distribution between plus minus a is 95%. To do this, this means 95% is in the middle And then the error probability 2.5% must be put on each side. So underestimation probability 2.5, overestimation probability 2.5. So you have to find top 2.5% value or from the bottom. So remember, we did it. We did this in the previous chapter, or at that time, we could do it this way. We want to find A that satisfies 97.5% as a cumulative probability. Cumulative probability at this point must equal to 97.5%. And then use Excel or calculator, normal distribution calculator. Then you will find 1.96 as the answer after rounding up to the second, at the second decimal place. Okay, so therefore this means plus minus 1.96 contains approximately 95%, which means this guy has the same structure, so this value must equal to 1.96. That's how we proceed in the chapter 6. So in the end, we have to equate these two guys. M over sigma over square root n equals 1.96. And remember, we are solving for m, the margin of error. What we need is the margin of error. So this is the solution. This is the solution. M is 1.96 times standard deviation of a single observation divided by square root of n. So okay, 1.96, not a problem to calculate. Sample size is known, so not a problem. But the problem is the standard deviation of a single observation. Standard deviation is need another estimator. So we need to estimate this. Usually we use this estimator, sample standard deviation estimator. So denominator is 1 minus n, like n minus 1, excuse me. So if you calculate, after calculating the standard deviation, plug that into the formula, then all the numbers are calculated from the sample, right? So number is known number, and sample size, you can just count how many observations, and standard deviation, calculate from the sample. So then you can calculate m, then you can calculate the confidence interval. So in the end, the formula is pretty simple. And usually in practice, as a rule of thumb, the 1.96 is approximated by 2. So plus minus 2 s over square root n is commonly used. So 2 is used as an approximation to 1.96. Now let's generalize it. We don't need, like, the confidence level does not need be 95%. In general, it could be anything like 1 minus alpha. Just choose whatever error probability you are willing to give up. And then, so 1 minus alpha must be the probability containing the true parameter between x bar plus minus m, right? And then, so this is the clue. From this equality, we have to solve it for m. So alpha is chosen, and mu will be cancelled out, and m is what we want to know. We know the distribution of x bar, so you can solve it for m. To do that, standardization, typical standardization, which cancels out the unknown parameter mu, and we have the similar form here. Now, then, you have to find a value a that satisfies this equation. So probability between plus minus a must be 1 minus alpha on standard normal distribution. In other words, overestimation and underestimation probabilities are like alpha over 2 each. So alpha is the total error probability, but half of the error probability must be put on each tail, on each side. So then top alpha over 2 probability is this value. This value is top alpha over 2 probability from the standard normal distribution, which we denote in this way. Small z, lowercase z, subscript alpha over 2. And then this is the clue, how we calculate, how we find this value from the CDF of standard normal distribution. And then, anyhow, we use this notation. So m now becomes z alpha over 2 times standard deviation of a single observation divided by square root n. And then this is margin of error. So x bar plus minus the margin of error is your confidence interval. Okay, so in the end, the derivation was a little bit tedious, but it's kind of collection of everything you learned so far. So you have to fully understand what you have done in the past. But even if you could not follow the derivation, the result is clear and simple enough. So you can calculate like all of the things like x bar, sample average, easy to calculate, s, sample standard deviation, easy to calculate, sample size, of course, known, and you just need to practice, exercise, do some exercise, how to calculate this value from the standard normal distribution calculator or Excel. So that's all. In the end, that is all you need to know. Okay? And there are only 4 components you need to know, and usually this is where most of you make mistake. So to see how to calculate this, go back to chapter 6 about normal distribution and review that part, how to calculate this, and try it by yourself. Okay, then look at this. So x bar is the center of the interval. So, but x bar does not affect the margin of error. Margin of error does not depend on x bar. So when x bar changes, the interval shifts parallel. Like width does not change. But when the standard deviation increases, standard deviation means the variability of the data, original data. So when S is large, the standard deviation is large, that means there is more noise, more uncertainty from the data. So your estimation is less accurate, or you have to allow larger margin of error. So your interval will be wider when the standard deviation increases. And third, imagine what happens if the sample size increases. So if the sample size increases, this part increases, it's in the denominator. So the margin of error decreases when sample size increases. So margin of error decreases means you can make your interval more accurate, more informative. You could do that because you have more information. Literally, more sample size means more information. So you can be more confident even with smaller margin of error. Finally, so z alpha over 2, it's about confidence level, or it's determined by alpha, which is the error probability we are willing to give up. So I would allow 1% error probability or 5% error probability. So the larger the probability, the width of the size of the margin of error is determined, right? So there are only 4 components that affect confidence interval. So it's pretty simple to calculate. Okay, and these are common numbers used for z alpha over 2, z values. Like in our example, 95%, it was 1.96. But when you have 99% confidence level, then z value must become larger. You have to allow larger margin of error so that you can contain more probability. So the number becomes 2.58. You may just memorize it, or like in doing the homework, you may need this number. Then just use this number. Like, right? But if you allow larger error probability by reducing the confidence level to 90%, you don't need that much large margin of error. You can make the margin of error smaller because you could sacrifice more outside probability. So the z value becomes 1.64. So remember, maybe it's not bad idea to memorize those numbers for your homework. You are going to use those numbers in your homework. So anyhow, you will need this table. Like, and what you need is the confidence level and the z value. So this in the middle are the process to find out those values. So if you have a different confidence level, you will need to make a different number, of course. Okay, this was another long video and was a full derivation of confidence interval. I'm not going to ask you to derive the margin of error or confidence interval in the homework, but at least you need to know how to calculate the confidence interval because it's simple enough. Okay? Okay, so I will bring another example in the next video and I'll continue in the next video. See you later.